Good morning. Yeah. And today we will learn a little bit of defense and then more learning about how to defeat or such things. But yeah, I believe this is the first time we learn about the defense. Yeah, so defenses are very important. So please keep that in mind. Like the reason why I teach attack is to learn about what attackers are doing and thinking. And then at the end, we need to use the same skill to defeat such attack. Yeah. So the topic for today is called the DEP, Data Execution Prevention, and the stack cookie, which prevents a buffer overflow attack. But don't get disappointed, but I will teach you how to avoid like all such tricks. And then these tricks are developed in like the 1998 and then 2004, that kind of time frame. Yeah. And then like right now it's applied to the almost all kind of the systems born after that. So not only for this laptop and this cell phone and the Linux, Windows, yeah, most of the every single computers are enabled with the DEP and stack cookie. And before getting into there, let's do a short recap about how we can run shellcode. So with the buffer overflow attack, it's something like we can fill the buffer, and then if we overflow that, we can alter the control data, such as save the DEP, or if we can directly overwrite the return address, we would like to do so. And after doing that, in all of the challenges for the how we can use shellcode, that requires you to put your shellcode somewhere in the stack, and then you write this shellcode, and then after writing that, put that onto somewhere in the stack in the program's memory, and then we can jump to there. Then it executes your shellcode. But then let's think about how we can defeat such attacks. So there are several defenses are available. Yeah. One is, so the problem is buffer overflow, not about the shellcode and another thing. If there's no buffer overflow vulnerability, then we attackers, as an attackers, we cannot even have a chance to run the shellcode. So that's the fundamental defense. So the first thing we will go over is like the how we prevent buffer overflow fundamentally. Yeah, and then you will learn we can do that, but that will slow down entire system a lot. Yeah. And because of that, so several software vendors, they care about the performance because that affects on the usability a lot. Yeah. And they don't want to use like the super slow defense mechanism. Yeah. In somewhere, for example, so some of the systems that requires a super high grade of security, in some of the 3-letter agencies they are using, or some of the nuclear weapons that some of the nation state has it. Yeah. They might want to use like even if like the software is 100 times slower. Yeah, they want to verify everything. Yeah. So in some cases they are useful, but they're not for our regular machines. So I like StarCraft and the StarCraft 2, that kind of a video game. And then if there's some delay, yeah, I don't want to play. Yeah, that's the thing. So the second part is like the second direction of the defense is like that we can make it's something like that we do not remove the buffer overflow vulnerability. Let them do that, but we raise the bar to make hackers annoying. Yeah, and then making exploitation difficult. Yeah, but it could be inaccurate. There could be some to hole, but it'll be super fast. So to give the little bit of number to prevent the buffer overflow entirely, your software will be 2 to 3 times slower. That's the state of the art. And for the making exploit hard, they incur like a 1 to 3% of overhead. It's something like adding 200% overhead versus 1% of overhead. And then with the 1% of overhead, if we can kill a lot of attack, why not use that? So we call that like something like economic decision in making defense. And we will learn about the both side of that. So although we go over like the fundamental defense, we will mainly focus on the second part, and they are so-called exploit mitigation. So we are not preventing the vulnerability, but we are mitigating the effect of the exploit, so making exploitation hard. So to let the attackers go away. Yeah, our systems are very annoying. Do not attack. So we are doing something like that. So specifically, we will learn about the techniques such as data execution prevention. So from the name, you can immediately feel that the shellcodes are injected into the data space. So if we prevent execution on the data, then you cannot use shellcode. Yeah. Don't blame me about it in that case. Why did you teach about how to write shellcode? But there are some of the cases we can reuse that again with some of the tricks. So that's the essential trick. So trust me about that. And then we will learn about the stack cookie. So that'll be another annoying thing in this week's challenge set. But after 2 weeks later, I believe like you all think that stack cookie is silly. Yeah, that's what I want to see. That's my goal. Yeah. And then the last one is like ASRL, address space layout randomization. And what it means is that, so I believe some of you have struggled with finding the address of the shellcode or like those kind of thing while you are conquering the challenges in week 3. But what the system will do is it will randomize the address space at each time of the execution. So even if you get the exact address on the core file, on the next execution, your address numbers will be totally different. So that's how we can make the easy defense, but making hackers annoying. Yeah. And let's get into more details. So for the fundamental defense, we will learn about the so-called base and bound check. And what that is very simple and naive. So whenever we allocate the buffer, the compiler already knows the buffer size. That's why they can compile it as a EBP minus 0x88. That's where the buffer need to be there. And then they know the buffer size must be 0x80, the 128 bytes. Then if we know that, why not include some of the code to check if any kind of the input receiving functionality stores more than the buffer size. So it's the protection will be going through like the overflow and then underflow, the bidirectional. So it is so-called, that's why it is so-called the base and bound check. Yeah. And this is a fundamental defense. And then if implemented, we can 100% kill the buffer overflow vulnerability. And then the next one is a stack cookie. It's an indirect defense. So we are not defeating buffer overflow attack, but it will prevent overriding return address. It will restrict you all and then other hackers for overriding the return address easily. Yeah. And the last one is data execution prevention. We will learn about how the system designers defeat executing of the shellcode and then getting back to some sort of the Harvard architecture. So I explained about the von Neumann architecture and the Harvard architecture. So yeah, the genius von Neumann won the thing. So like now all the systems are von Neumann architecture, but still we need the concept of the Harvard architecture when we take care about the security. Yeah. So never ignore the old knowledge. That's another lesson here. Yeah. Any questions? Yeah, I didn't teach anything, so that's there's no question, right? Yeah, let's move on. Yeah. So we called base and bounds check as a spatial memory safety in academic term. Yeah, it looks like very academic term, right? Yeah. The reason why it called as a spatial is, so think about the memory space, and then we allocate the buffer, and we want our input does not go over some of the bound, does not go under some of the base. So it's about the space of the memory. That's why it's so-called spatial memory safety. There is a different class of the memory space safety, so-called the temporal memory safety. That is more about the analog and free, those kind of the dynamic memory management. We will learn a little about that at the end of this course. Yeah. So please keep that in mind. We have a spatial memory safety and the temporal memory safety, and then right now we are learning about the spatial memory safety. So the purpose of doing this is just mark all the base and bound at any of the memory allocation, and then enforce that when we store any kind of bytes, or when you read any kind of bytes out of the memory. So how we can design this kind of thing in a very naive way, is we can use a fat pointer. And the reason here why we use the keyword fat is a pointer is just pointing an address for a buffer. But in addition to that pointer, we will use triplet of the pointer to store the pointer itself, and then what is the base pointer of the region, and then what is the bound pointer of the region. So what we want to do is like set the base and bound, and then any memory access over or under this, like the base and bound, we would like to kill the program. That's how we defeat all kind of the buffer overflow attacks. And to do that, there is a thanks to the develop the compiler techniques. So in old days, it's very hard to make changes in compilers such as GCC. But with the advance of the LLVM, have you heard about that tool? So have you heard about the Clang compiler, CLang? So that is based on the LLVM infrastructure. And then what LLVM does is like that they decomposes the whole entire like a compiler steps as we call it as a front end. So the front end means like the language that human uses, not the natural language, the programming language. So C, C++, and then Java or some other languages, Fortran or like those kind of the compilable language. And then that's the front end. And then what front end does is just parse the abstract syntax tree and then understand what the program wants to do. And then in the middle end, there are the techniques that like we actually lift this kind of the human written programming language into so-called intermediate representation. So that's the so-called LLVM IR, LLVM's intermediate representation. So it's something like no matter what kind of language you use, we will translate that into the central language, and then we will do optimization and then all the other stuff. And then at the back end, there are CPUs. So what if we would like to run it on the x86? Or what if we'd like to run this program on ARM machines like this kind of the device? So at the back end, we can choose one of the architecture, and then it will lower the high level language into the binary. So that's how the LLVM compiler infrastructure is designed. And then after that design was announced in like the 2003 or something, so that developed with the super high speed. So like the GCC also changed it like that. So the reason why I explained this is like we can implement this kind of the base and bound check in the middle end of the compiler infrastructure. So programmers do not have to do anything. And then if we rewrite some of the program that insert that transform any kind of pointer as a fat pointer, and then do the base and bound check in every memory access, that's quite neat and possible. So I believe like if you want to for like I believe like right now it's a scope of like the senior project, I believe. So you can try that if you are adventurous. So that you can set it your goal as defeating all buffer overflow vulnerability. I want to implement that. So that's quite not that difficult, and then it's a less than 1 year project, maybe 6 months or something. So please think about it. So thinking as we implemented something in the compiler, then whenever there's a pointer, we can add like a base, a bound. So don't care about the naming. So we can use like any kind of the abstract name and then like the pseudonym in the compiler. So, but I would like to conceptually deliver how it works. And then how we set the base and bound is, suppose we allocate memory with the Hammerlock with the 512 bytes. Then we need to set the base as the pointer itself, because pointer will point to the start of the memory, and then bound as a plus 512, because that's the length mentioned in the programmer's intention. So compiler automatically insert these two lines right after the MLOC call. But please think about that this kind of thing is not done in the C language. So C language will be lifted as a LLVM-IR, and then in the LLVM-IR we can insert that, and then we will lower that to the x86 binary. And then what it will do is every time the program accesses the memory, so it will allow 0, 1, 2, and then until up to 511. But if they are okay. But if the program wants to access a 512, then we will check if that is going over the bound. At the same time, we should check if that is like under the bound. If it is, then we should kill the program. That's how it works. And then it also works for the underflow. It tries to access the out of base. Then we can compare the index and then pointer, and then we can check it. That's out of bound, and then kill the program. And this is like how we created the triplet of the fat pointer, and then how we allocate. And then to make it work for the entire program, we need to have some of the propagation rule. So what that means is that whenever we assign a pointer to the another pointer, then we need to assign the same base and bound. Then it will be propagating, and then at the end, if we have any kind of pointer, they will have a base and bound. So suppose we set the B to point like start of the memory address pointed by A, the same as the base. And I want to give another example. So suppose we would like to set the character pointer C as the 2 byte shifted from the start as like the B2, at the address of that. But in this case, although we change it like to see where it points from like a start of the buffer, but we don't change any kind of thing about the base and bound. So for the propagation rule, we just propagate base and bound as the same value, because base and bound has never been changed. And then let's take an example. What compiler need to insert another check when we access the memory. So at the allocation, we need to set the base and bound. And then at the assignment, we need to propagate the base and bound. And then at the access, we need to enforce base and bound. So suppose we access a C indexed by 1. And then that's actually because a C is like the B plus 2 and then A plus 2. So that C plus 1 is actually B plus 3 and A plus 3. And then that's definitely within the base and bound. So compiler, whenever they see this kind of the code, it will insert this kind of 2 if condition. If the index is it should be equal or bigger than base or lower than bound. And then you can feel it why I mentioned about like this kind of thing will make the entire system slow down, because whenever you access the memory, it will run 2 if condition. And then when we try to access a C510 as an index, so that's actually the equivalent to the A plus 512. Actually, that's a 1 byte out of bound. So then in this kind of the inequality, that will never met. So we can kill the program. Any questions? So it's very simple, right? And then it is mathematically proven that we can kill all the buffer overflow attack with this one. And then this one is developed in 2008 and 9 timeframe, even if it is very simple. And then I believe that's because like thanks to the compiler techniques beforehand, like it's very hard to implement those kind of thing. So the LLVM was one of the master student thesis from the University of Illinois. That's amazing. Then that master's thesis changed the world in 2003. And then later, academic researchers take into like implementing these kind of thing, yeah, in LLVM compiler. So that is published in 2009. Yeah. So it's all about the base and bound check. So it also applies to the buffer. So I just mentioned about the able to store byte by byte. And then so even if we insert string copy of this kind of thing, so internally string copy will have a loop. Yeah. What they do is just treating anything with the 8-byte integer in 64-bit machine, because that's the faster way than like storing the byte by byte. So dividing it by like the 8 and then copy all the thing. And then for the last few bytes, and then they write it as a byte by byte. And then in any case, we can insert these kind of the compilation check, and then we can check the base and bound. And this is actually how Java and other Python or some of the memory safe languages protect against the buffer overrun. And then these techniques are doing the same thing in C and C++ level. Yeah. And then if you're familiar with the C++ standard template library, there are some of the data structures called the vector set, or like those kind of the some of the data structure that manages memory safety. And these are all doing this kind of check internally. So this is the academic paper that I mentioned. So like researchers from the University of Pennsylvania, yeah. So these guys implemented the techniques so-called SoftBound. And then the reason why it is so-called SoftBound is that there's another paper called hardbound. So because it's too slow, yeah, they realized that. So they published the hardbound first. They implemented base and bound check in the CPU and then evaluate the performance. Yeah, I'm not sure about the numbers, but the numbers was 60, 70% or something. So it's a slightly much better than the SoftBound, but still super slow. And then you can also think that the changing hardware is difficult, but changing software is easy. Just clone from the GitHub and typing something, and then you can do that. But to change the hardware, you need to have a super big fabrication building kind of thing, right? So that's why we'll always love the software solutions first, but it's quite interesting. They published the hardbound first and then softbound later. And then another interesting thing was like I started learning about this kind of the hacking stuff starting 2008. So my personal experience was like at that time, I just finished my mandatory military service, and then my brain was cleared. I know almost nothing. And then I applied for the internship at Google Korea, because like at that time in South Korea, they just pay the internship for like the $1,000 per month. But the Google Korea, yeah, they follow what Google does. They pay $3,000 per month, and then they support all the foods and the thing. Yeah, I really want to get it. Yeah, so that there's only one position available. And then I went to interview, but even if I don't know anything about hacking, those kind of things, I was just like I was not like this. I was just a very like the candid student, and then want to learn everything and then just study hard. So like I was confident of like algorithms and those kind of stuff. So in the interview, yeah, I nailed all the questions. Yeah, but I couldn't get the position. Do you know why? So the other candidate, he's a medalist of the International Olympiad in Informatics. Yeah, so #1 guy in the like that kind of algorithm challenge, and then even if I can do well in the interview question, they love it. So I thought that, oh, this is not my way. And then what do I do better? And then what do I do good? And then so I was very good at lock picking and then those kind of thing. Then how about doing that in computers? And then that started my journey. And the reason why I'm telling this is like after starting learning hacking in 2008, the first academic paper that I read is hardbound. Yeah. So the hardware solution for defeating the kind of thing. And then at that time, I decided that I want to go PhD program, because PhDs are doing this kind of thing. So cool. I want to do that. Yeah. So these line of the papers changed my like the career goal. Yeah. So like I just want to share that, and then I also hope like I would like to inspire some of you guys. I'm not telling you to PhD, but but the change. So think about like if the techniques are so cool or something, and then you can also do that. There's nothing impossible, and then I'm keep teaching that, right? Yeah. So I just want to share that. So in the paper, so when you start reading academic paper or something, there are so many texts. So it could be a little esoteric with some of the proofs or like the sophisticated mathematical formula or something. But the good thing about the academic papers are like they are very structured for someone who cannot understand the mathematical proofs. They don't have to read it. So I'm not a mathematician, so I also read like part of that, and then these are the part of that I like. So whenever there's a location, store base and store bound. Yeah. And then if the pointer is null, there's nothing about that, then we set the base and bound as a null. And then if there's an array, if we store the array into another pointer, then we set the base and bound accordingly. And then we propagate that, and also whenever using like this kind of rules. So these kind of things, I believe like the sophomore level undergrad students can understand this, right? So that's the beauty of the academic work. Even if like that looks super sophisticated, that's the job of the PhD. But they are doing it very good at writing. So if you take a look at the academic papers, there are parts that even undergraduate students can understand, like this kind of code. Yeah. So whenever you are curious about something, you can always find some of the academic paper related to that topic, and then don't be afraid or get hounded by like reading academic papers. Yeah. And then you guys now can read x86 assembly well, right? Yeah. So with a little bit of practice, yeah, you can read it and then learn it and do many things. Let's talk about the bad things about this work. So after I read both of the papers, I also had a mixed feeling. So the technique is good, but it could be super slow. The reason is, so whenever we have a pointer, we need to store 2 more data. So we need to actually 3 times of the memory is required to store the pointer. And then what that matter is that, so in the CPU, we use a cache memory to have a fast memory access, and the cache memory size is limited. Still the world fastest like a desktop computer, it only has a 64 kilobyte of the L1 cache. Yeah, so that's quite small. But if we use this kind of scheme, fat pointer, yeah, then we will use 3 times more memory. Yeah, just storing the pointer. It will pollute cache. Yeah, then that will affect on the performance. And then whenever we assign one of the pointer, we need to do 2 more times to do that. And then we need to insert 2 comparisons on every memory access. So that actually affects the performance degradation. So this is the performance graph extracted by the SoftBound paper. And then for just take a look at the highest overhead. Yeah. And then because they do a little bit of optimization, but that optimization is a little sophisticated to kill the scalability of the program. So like better to focus on the highest number. So for some of the programs, it gives like a good performance number. So the programs here are so-called benchmark programs. So there's a benchmark called SPEC 2006 or SPEC 2017. Have you heard about those kind of thing? Yeah. So those benchmark sets are like composed with the various programs as a representative set of like the programs that we are using every day. Yeah. So to give a summarized performance effect on like whenever we instrument some of the program. So for this kind of program, they are fast. Do you know why? They don't do much memory operations. They won't spend most of the time just calculating. That's why. But these kind of applications, they use a lot of memory access. Yeah. So these are slow. But in average, we can see around 100% to 200% overhead. Yeah. So that means like this technique may slow down your computer to 2 or 3 times. And then we should always think about the security versus performance, as I mentioned about something example of the nuclear weapon kind of thing. Yeah. So even if we can get the 100% buffer overflow free, if it is too slow, then the technique may not be adopted. So the picture that I pasted here is about like some of the YouTube video that benchmarks which cell phone is fastest for booting. Yeah, they do that. And then you all know that the battle between Samsung and Apple, yeah, they want to sell more cell phones, right? And then after seeing this, the Samsung say, oh, 100% buffer overflow free, but your boot time is 3 minutes. But the Apple say, oh, yeah, we have a good privacy. We don't know the detail. We will not disclose the detail, but our boot time is 10 seconds. But then most of people will go for the Apple. Yeah, right? Yeah. So there's that kind of usability and then security performance, a trade-off kind of thing. So as a system designer, we always need to think about the performance effect on the system. And then if that kills the usability a lot, then that's the solution in the academic paper. And then that cannot be implemented in the real world. Yeah. But in some cases, in the nuclear power plant or like some of the security critical infrastructure, so even if that is slow, we want to use that. So there are some cases like those super slow implementation can also excel. Yeah. So please keep that in mind. That. So we learned about the base and bound check, and any questions for that before moving to this exploit mitigation? Great. I feel like I teach well today. So the next topic is an economic defense. This is the topic for week 4 challenges. So the first economic defense that I will introduce is so-called stack cookie. Yeah. And then it is just a random number put on the stack. And then the purpose of this is like in 1997-8, yeah, there is a hackers magazine called Frack. Have you ever read that? It's PHRACK, Frack. Search about that. Yeah, you will see the lots of like text documents that describes hacking about the hacking. Yeah, so there's an article called exploiting the buffer overflow vulnerability for fun and profit. Yeah, that was the seminal article that enlightened all the hackers work on that, and then the entire internet and then the computer world was mess. Yeah. So right after that, in 1998, yeah, researchers developed the techniques so-called stack cookie. But at that time, most of attacks are buffer overflow, not the underflow, mostly overflow. Yeah. So I just want to deliver some of the context about how this defense was developed. So what it does is, so it will allocate buffer, but at the end of the local variable region, right before the control data, including save DEP and the return address, we will put the random value at the function call. So after storing the return address and the save DEP, we will put the random value. It is 4 byte in 32-bit machine, and then it will be 8 bytes in the 64-bit machine. And then we will just let it run. So suppose attacker overwrite this buffer, then if they smash the cookie with the AAAAA or something, so at the function return, we will compare if that value is same as the previous value. If it is not, we will kill the program. So this is another simple defense. And then you will see that what we need to do is getting one random number at the function call, and then checking one if condition at function return. It's not about the single memory access or assignment, those kind of things. So we don't care about what the function does, but we will check at the entry and the exit. So that's where the performance gain comes in, and then you can immediately feel that, oh, that will be much less number of the comparison and then operations. Yeah. Then let's take a look at how it works in visually. So suppose we have a string copy, and then to the buffer, suppose we put like these kind of value to overflow the buffer. And then DD will smash the cookie, EE will change the EVP, and then we would like to put the address of the getter shell. Yeah. But before function returns, we will compare the cookie value, the global, to the stored cookie value. That's not equal, so we can kill the program. And then I am a hacker at the same time. I'm an academic researcher, so I have to present another academic paper. Yeah. And then this is developed locally in Oregon. Yeah. So have you heard about the Oregon Graduate Institute of Science and Technology? This is a university, but it does not have an undergrad program. It only has like a graduate program, and masters and PhD students are working together, and then close to Intel, and then Intel and this institution worked hard to develop a lot of techniques. But do you know why we are not seeing that school again? So after 9/11, US government cut all the research funding, and then that school was operated with the research funding because there's no tuition income. Yeah. So school was collapsed in 2004. That's unfortunate. Then that's why I always use Google. Yeah. So another thing is like this guy, Jonathan Walpole. Yeah, he's still in Portland State University. And then this guy, Crispin Coleman. Yeah, after his graduation, his PhD, he hired at the Microsoft. And then at the Microsoft, he implemented this technique in the Visual Studio. Yeah. So I'm still keep advertising about the PhD program. So if you do PhD, then like this guy, you can develop this kind of technique as a paper, and then go industry, and then you can change the program, and then every single developer will get benefit from your technique. Yeah. So also, I don't like a lot of text in an academic stuff. Yeah, I just exhibited like this kind of graphics, and then you will see that from the buffer, if there's a canary word, and then so in this paper, stack guard, they call it stack cookie as a stack canary, and the reason is in old days had the excavation mining for the coal mining. So coal miners use brought a canary, the bird, into the mine, and then because there are chances that they would have like a carbon monoxide, and then bird dies faster than human. So if the bird die, everybody need to evacuate it. Yeah. So it's an indicator about the dangerous stuff. I don't like that kind of cruel thing, but yeah, in the virtual world, we use the word stack canary. So we put the stack canary, and then if the canary dies, then something dangerous will happen. So we will kill the program. That's the intuition. Yeah. So stack cookie was first implemented in Visual Studio, but I don't like proprietary technique. Yeah, I always love the enthusiast for the open source and the thing. So that's why I introduced stack cookie in GCC. That's open source. And then that's so-called pro police. So police for enforce something. Yeah. And then, so suppose we compile this code, yeah, with the regular option, because now it is enabled by default. And then this is the compilation result. And then we will see some of the part added, and then we have never seen in the disassembly of the week 1 and week 2 challenges. So this GS0x14. So this is a special way of the accessing some of the memory. Yeah. Then you can just regard like it fetches some of the data GS over 14. Yeah. So that actually fetches a random value generated at the starting of the program and store that to EAX and then put that on the -0x3 on EBP somewhere here. And then do XOR EAX to clear the EAX value, to not let the attacker reuse the random value. So the random value is stored into the stack. And before the function return, so the stack cookie was EBP -C, fetch that, and then do XOR with the value of the random value. And then if it is 0, then it jumps to the 70, leave return. The XOR 0 means that the two values are the same. But if they are different, then they will call stack check fail and then kill the program. So important thing is no matter what function does internally, it will just insert two parts, put the value, and then check the value at the function exit. Put the value in the function entry, and then check the value at the function exit. So you can play about this slide like this. And then for the one of the program, if this is some of the program that I like just copied from the one of the hacking competition called the CTF Challenger. Yeah. And then if I try to trigger the buffer overflow attack, the canary dies. So it says stack smashing detected, and then the program will be terminated. So let's think about the stack cookies overhead. So it involves two memory moves, random value to the stack. And then at the end, stack to the register and then compare with the random value. So two memory move, one compare. So that is applied for per each function call, not about the per each memory access. So I ran the spec 2006 a benchmark for this. And then you will see that the F no stack protector means that there's no stack canary. F stack protector means that the protecting all this like the functions, even if there's no buffer, because I want to see the worst case of overhead. And then the worst case overhead is around 4 to 5%, but the practically in these days, like the overhead is around 1 to 2%. Yeah. So that's why this technique is immediately adopted to the Microsoft and then GCC and then all the other compilers. Yeah. So after we learn about this thing, we will have challenges. So I prepared 4 challenges for stack cookie. So that right now you cannot see the challenges on the CTF, the website, the scoring website. So I was lazy. I need to do that like after like finishing the lecture. Yeah, but the challenges are available on the server. So high performance, like go ahead. Yeah, so just fetch week 4 and then start solving. But yeah, for the others, I will guide you how to solve that in the slides. Yeah. So first one is a very naive stack cookie. So it will have a fixed value. You need to just get that. So this stack cookie one is not the real compiler-based stack cookie. I intentionally wrote it something similar to buffer overflow level 4. It checks about the return address kind of thing. Yeah. So that I intentionally wrote about that. So this is an easy challenge. And then try to get the concept about the stack cookie at there. And then the second one is also not about the compiler trick. I will use random value. Yeah. But you can also defeat how rand works. Yeah. So it's all deterministic. It's not the pure random. Yeah. So please think hard to defeat the random cookie. So it's just like you will fill the buffer, but if you know the value, put the same value as before, and then overwrite the address, return address. Then it will never detect the attack because it only detects the random value changes. And then stack cookie 3 is about the bypassing propolis. So bypassing the real defense. And then how you can do that is you can read some of the content. So right now learned about how we overwrite the buffer and to overflow the buffer. But the buffer overflow can happen for reading too. So you can read the canary value by overreading the buffer. And then when you overwrite the thing, put the same value back and overwrite the return address. That's the exploit sketch. And then stack cookie 4, there's no leak. You cannot read the stack cookie. But there is a way you can still guess the stack cookie with a little amount of the trial. And then next set of the slide will guide you for that. So let's start with this, the weakness of the stack cookie. So for the stack cookie 1, I just put like this kind of the cookie value. Then what you need to do is like read the disassembly, get the value. Then when you overwrite the buffer, put the same value back here, overwrite E, and then return address. Then comparison will be passed, and then your attack will be succeeded. So the lesson is simple defense can easily defeat it. Yeah. And then in the stack cookie 2, I will put the random value here, not a fixed value, but you can guess the number because to use a rand, we need to run like the srand to see the random value. And then if you use the same seed, then you can guess what will be the random value, and then you can put the same value there. So to do that, you can refer to how you can guess the next random number, and please try that for attacking stack cookie 2. So these will be simple challenges. So these are very effective to sequential buffer overflow. And then because like if you can like point this address without overwriting this in the program, then stack cookie is not effective. Yeah. So this is effective for like common mistakes, something like we use string copy, mem copy, read, scanf with the unknown size. Yeah. Because it will sequentially overwrite starting from here up to there. So with these functions, if you can overwrite the return address, it is guaranteed that you must touch stack cookie. Yeah. But one of the weaknesses is that if we can change the index, yeah, then after override, so suppose the local variable index is here, yeah, then you can change the index to skip this kind of part and then just overriding the return address. Yeah, that's possible. Yeah. That's the cookie 4. Yeah. So you need to skip the overriding stack cookie and then overriding this one. Yeah. And then for stack cookie 3, I believe. Yeah. So these are all 32-bit machine. Yeah. And then think about the 32-bit random value. So suppose you don't know the random value, then one dumb exploit could be fix one number and keep trying. Then luckily, the random value could be the same value as your guess. Yeah. Then what is the chance? So the 32-bit random value can have like a 2 to the 32 cases, and then that's a 4.2 billion trial. So if you try your exploit 4.2 billion times, you can win. Do you want to do that? How the better purchase Powerball, right? Yeah. So this seems super secure. If you don't know about the random value, you need to try it 4 billion times, and then in 64-bit, that's a 2 to the 64, even larger. And then like what is that? This 18, like more than trillion is zillion or something. Yeah, right. Yeah. So you can never finish it in your lifetime. Yeah. So it seems super secure. Yeah. But there's a way that you can leak the value. So you cannot leak the value, hide back in the over like a GS register. But what you can read is like you can read 0xC EBP because that's on the stack. So if you use the print functions and then do not put any kind of 0 here, then it will regard, oh, string never ends, and keep printing. Then they will print out cookie. Then you can get that cookie value. And then when you try to overflow the buffer with the override, put that value back and then change the return address. So that's the one way of solving the challenge. But in stack cookie 3, I intentionally removed that kind of the leaking function at all. So there's no leak, yeah, because challenge might be too easy. Yeah. So the challenge is that you need to guess the random value, but I don't want to make you to try the 4.2 billion times. Yeah. And then actually you can defeat this challenge by just guessing the random number, yeah, less than 1024 trial. Then let me explain how you can do that. And then one condition is that the application must use fork. And then how many of you know about what is fork? Yeah, so the fork system call, what it does is like a cloning that process the same thing as a two thing. That's why it's a fork. And then two programs must have same state. That means that cookie value will be all same. Yeah. So it's something like fork and test. And then if it die, oh, my guess is wrong. And then do that again. But we will do that 1 byte by 1 byte. So we will guess 256 times for 1 byte. And then after matching the last byte, move to the next byte, move to the next byte, move to the next byte. That's how we can guess it in the 10,024 times. And then there are more slides, so don't worry. Yeah. So suppose we use fork, then on the left side, this is the original program. And then on the right side, you can regard this as a child program. They're having all same state. And then stack cookie values are same for the entire, all the functions. Yeah, it will only use one random value for all. So if you can guess with the child process, and then that will work for the parent process or future child process too. And then this kind of design is widely available. So for the desktop applications, they do not use much fork, but whenever you connect to the server website, they fork and serve, fork and serve, fork and serve. So you can defeat Nginx web server if they have a buffer overflow vulnerability with this technique. And then some attackers indeed use this technique to defeat the Nginx buffer overflow vulnerability. Yeah. So I have to say, don't try this at home, but try this in our server. Yeah. So how fork works is like whenever a client connects to the server, fork and serve, fork and serve, fork and serve. They all have like a same cookie value. So we will exploit that. So our assumption is that the server program contains a sequential buffer overflow vulnerability. And the server program uses fork to serve a client. And if stack was smashed, the default behavior is that they will kindly let us know stack is smashed. If we see this message, then your guess is wrong. If we cannot see that message, your guess is correct. So we have an oracle to tell that your guess is true or not. Thank you so much for the GCC Propolis. Yeah. So how we can do the attack is, suppose the cookie value is this one. So what we will do is like a guessing for the 256 times, override, 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 and then just override the last byte. Stack smashing detected. Stack smashing detected. Stack smashing detected. But for this value, you will not see the message stack smashing detected. And you can successfully guess the last byte. So this is the indicator. Yeah. And then now we know that the last byte is the 89. Build a buffer like this. And then guess, guess, guess. Then eventually we will make the right guess. And then do that one by one. After guessing 4 bytes, overwrite the return address. Quite neat technique, right? Yeah. So that thanks to the oracle that tells like the is it correct or not. So the hackers always think that like they want to tame the computers. Computers are dumb. So tell me the truth. Yeah, we can do that. Yeah. So this is so-called the side channel attack. So although the program will never tell the random value directly, but we will construct information leak like this. This is just 1-bit information. And then we can accumulate that information to guess about like a full 32-bit, and then even for 64-bit, no matter how big it is, we can do that. Yeah. And then for 32-bit, it's to 1024, 64-bit, 2084, 85, 80, 48. This is much less than like the, what is that? The 2 to the 32. So it's similar to, we just applied the logarithm, yeah, to the attack. Yeah. So maybe you might want to ask like oh, this is super insecure, but why do we use it? Yeah, but this is better than nothing. And then this technique does not involve much performance overhead. We have that. And then this is actually very annoying in like the hacking. And then if you play CTF, you will realize that. And then you will realize that in the challenges. Yeah. Any questions about stack cookie? Nice. Then let's move to the next one. So next defense is so-called data execution prevention. I don't like this name because this is also proprietary marketing term from Microsoft. Yeah. And then there's another term called NX-bit. These are all so NX-bit or execution disable, XD. These are terms from AMD and Intel, all proprietary term. So you can think as like the no execution on data. Yeah, that may be better. Yeah. So the technique is developed with one question. You know how to exploit a buffer overflow vulnerability, then what is the next step? And then in the most of cases, you will never have a get or shell function. So that's why we learned about how to write shell code. And then using that, even if there is a no get or shell, we can get a shell like that using the shell code. So jump to the shell code. That's the next step. Then another question is, if we know that, why do we let the attackers run a shellcode? Block it. So think about it. When we compile the program, we know there's a code and there's a data. Then we will only execute the code. But why do we let our CPUs run on data? Yeah. So attacker injects a shellcode into the stack, heap, or anywhere in the memory, but the code area is read-only. You cannot inject the code. You can inject data. So shellcode will be in the data region, but why? Stack is executable. Simple, right? So if we make it non-executable, then we can win. So that's where we have this kind of diagram. Yeah. So that this is the Harvard architecture, and then this is the von Neumann architecture. So the von Neumann architecture is mixed with the program data, and then this is the modern computer. And in Harvard architecture, program the code and the data is totally separated. No matter what you do on the buffer overflow here, you can only taint the data, not about the code. So the code security is ensured in the Harvard architecture. And then, because our systems are insecure, we need some of the mixture of two. So before 2003, we cannot implement this because the memory protection mechanism developed by enforced by the CPU in Intel, both in AMD and in all the other CPUs, they did not have a notion of like the no execution in data because they studied about the thing in the textbook. Von Neumann architecture is great. Yeah. Don't care about the program data separation. Yeah. But later they realized that. So both Intel and AMD CPU at the same time, they changed their page table entry. So page table entry is something that we use for checking the privilege of the memory. You will learn more about this if you take a CS444 operating system two that I teach. Yeah. So these are the bits that we can use for the privilege enforcement before 2003. So there's a valid bit. Valid means that we can read. And then there's a write bit. Write bit means that we can write. But there's no bits about the execution. So in 32-bit computers, we already use all the flags. So there's no more space. We cannot do that. So when AMD extend their CPU to AMD 64, and also Intel follows their architecture to change from x86 to x86-64, because now the page table entry is 64-bit, we have more space. So they put the highest bit, 63rd bit. They set it as a no execute bit. So if that bit value is 1, then if the CPU tries to execute on it, then it will generate a general fault, protection fault. Yeah. So that's how we can make the stack or data area inexecutable in the operating system. So that is implemented in Microsoft Windows XP in 2003 or 4 first. So there are some of the options that turn on DEP or turn off DEP or something. Yeah. So just for the essential programs or all programs. So this is because like some of the programs, especially some games that requires a high performance, they use a lot of hacks internally. They are using like they are using mixture of the code and data, dynamically generating the code. So data need to be code. So some of the games can never execute if we enable DEP for all programs at that time. Yeah. So that's why there's an option. But then these days, all the programmers are aware of that. We should never do that. So there's no compatibility issue for now. So I believe all of your machines and the cell phones are enabled with this technique too. Then DEP is a marketing term of the Microsoft Windows. No execute is also a marketing term. Yeah, I just recall the term. Yeah, that I like. So in academia, we use write XOR executable. So if the region is writable, then we should remove executable flag. So to make it true, write is 1, then executable to be 0. Or if it is an executable, then write must be 0. So never let code region writable. That's the implication of the NX bit. And to check whether the executable stack or if the program has an executable stack or not, so you can use a program called read ELF. ELF here is an executable and linkable format. It's format for the binary for the Linux and Unix operating system. And if you do that, read ELF-A and then challenge binary. So if you try that on the Stack Overflow SC, because we will use a shellcode, so that is allowed for the execution on the stack. And to check the privilege level, so some of the addresses are around the 08048000. These are code area. Code area flag is with the readable and executable. You cannot write. You cannot change the code. It's secure. But there is a stack. Stack is readable, writable, and executable. That's why you can put the shellcode on the stack and then execute on it. So for that challenge, those set of the challenge binaries, I intentionally remove next bits as a 0 to let you execute on the stack. But in week 4, which is challenge set, there is a challenge for the DEP-1 to read that. So we will see that code area is read and executable, but the stack area is readable but writable, but not executable. You will never see both the writable and executable area. So you cannot use your shellcode. There's no getter shell, but you can still get a shell. Yeah. So now most of the programs are built with non-executable stack because that's the default option for the compiler. Because I intentionally need to use -z exec stack as a compilation option to enable that. Yeah. Then your question might be, in that case, how can we run system or execve or that kind of the system call? There's no program will never have the kind of function, and then program will never have a get shell. But right now, you all know that how you can call another function using buffer overflow vulnerability, and then in the program's memory space, they're already system execve, execl, like those kind of functions are already existing. So it's just a matter of the finding the address and then just run it. So we will exploit the existing code in the library space, and the technique is called to return to libc. Libc is a C library, and then if the program is written in C, it must include the C library. And then in the C library, they do have system, exec, set regid, get regid, those kind of functions. So we can call any function. So let me tell a little about the dynamically linked library. So when you build a program, when you write the program, you will, I believe most of you have never take a look at the implementation of the printf, scanf, those kind of things. You just use it. And then you don't even write it. And then the reason is the code is already there, and then we just including that into the memory space and then just use it. Yeah. So these functions are not implemented in the header. Header just sets a name. Yeah. And then these functions will never included in the program. So libraries will be injected to the processor memory by the operating system kernel. Yeah. So they just exist. You can reuse that. And then let's take a look at how a program is loaded. So whenever you execute one of the program, not about the shellcode or something, just execute the program on the shell or like by the command line or with the process in the Pwn tools. So the operating system kernel will get the request for the execve. Then it will load the target ELF binary first. And then it will parse the binary to see what kind of libraries operating system need to inject to the program space. And here, if you use the command called LDD, and then challenge binary, then you will see that the Linux gate is there because it's a 64-bit machine, but running 32-bit machine, a 32-bit program. So we should have this one. And then it has libc here. So the libc will be injected in this address space. And then there are LD Linux, and then LD Linux is a program that actually handles the loading of the older libraries. So operating system kernel will parse this information, and then according to that information, kernel loads the thing, prepare the binary, and then it will run start libc start main and main. So that's how main function starts. So many people think that the C program starts at main. No, yeah, it starts with the kernel and then load all the libraries and then start libc start main and main. That's what we need to know when we try to play with the program. So that is actually can easily be summarized by the strace call. So if you run strace is about this tracing all the system call. When we run the program, kernel loads the challenge binary first, and then it tries to check with some of the system settings for the library, and then it open libc and load to the memory space. So that is automatically done by the operating system. So the good thing is libc will be loaded, and then that will be in your program's address space. So we will be focusing on libc, and you can take a look at the directory here, right? So we will use the same binary. So if you open that with GDB and then type info functions, you will see that all kind of the available functions in the memory space. Yeah. So these are like a pthread and get or those kind of functions. So even if your program will not use those functions, these are available. Yeah. Then you might want to find system, then you want to directly run binsh or execve, then you want to do binsh 00, right? So in GDB, you can find that kind of functions. So let's do that. So if you open GDB with the challenge binary and try to print system, you cannot find that because there's no system function in the binary program. But if you set the breakpoint at main and run it, so at the runtime, now GDB knows that the libc is where the libc is loaded, and then if you run print system, then it will print the address of the system. So you can easily find that where the function is with this kind of technique. So attach GDB to the challenge binary, breakpoint, and run it. And then print system, print execv, print execl. Those kind of thing all works. And now you know where the system function is. Then you might want to compose your buffer overflow attack payload, fill the buffer, fill the EBP, and then put the address. So Intel CPU uses a little endian. So 40 comes first, 19 comes next, E4 comes later, and then F7 is the one. And then you can easily use P32. Yeah, that will do that little endian transition for you. Yeah, this will execute system function. But the problem is that it will run system function with weird argument. What we want to run is this one with the string binsh as an argument, or this one, string A, then we can use symlink, symbolic link tray, right? We want to do that. How can you do that? I already teach you. I already taught you, because we have gone through like how the stack invocation and then argument passing works. So theoretically you can do that, but I will not let you leave there. Yeah, let's take a look at this. Yeah. So this is how argument passing works for the regular program. So when we call the function, we store the return address, but at the time of call, at the location of the ESP, we have a first argument. Location of the ESP plus 4, second argument. So system function also assumes that, and if we put the argument at that position, then they will never know. Computers are dumb. They will just use that. So let's take a look what will happen when we overwrite return address as a system, and then how they fetch the argument. So the important thing is, like, when you start executing the system function, then it expects ESP is pointed by argument 1, but it will automatically store the return address. So actually, at the ESP, there should be the return address. ESP plus 4 should have an argument 1. ESP plus 8 should have an argument 2. Then let's start overriding like this. And then we will put the address of the system. And then when function runs relieve, EBP will be changed with weird value, but we don't care. But the ESP will be here. And then return is actually pop EIP. So when we get to the execution of the system, ESP will be here. Yeah. And then previously we had this kind of the composition. So when we get to execute of the system expects that ESP points to the return address. ESP plus 4 is the first argument. So ESP is now here. What is ESP plus 4? This one. So if you put the address of the BNSH at this location, then system will regard that as the argument. So we didn't change the code, but we know how system functions receive the argument. Then just put the argument at the right location. That's how we exploit the thing. So when we get to executing the system, the first one is the push EBP, and then move EBP ESP, and then reserve the stack for the local variable. And then in their notion, EBP plus 8 is the first argument. EBP plus 8 is this one. Yeah. So if you put the address of the string to the second argument position of the original function, then that will be regarded as a first argument to the system. And then let me provide more easier way to do that. So suppose there's a return address. Then how you can set the first argument is ignore the next byte, next 4 bytes, ignore about that. Because that's the return address of system. We don't care. Because the system will execute BNSH, will never return. Yeah. So put the address of the BNSH at the return address plus 8. That's the rule here. Yeah. And then that will be return address plus 16 for the 64-bit. Yeah. And then when running the system, push EBP, and then something like happens. So system will regard BNSH as the first argument. But suppose there's no BNSH, then system will return. Then where system returns. So this is the system's return address. Then after running this function, it will run printf. So can you see that we can call one function and the other function with this kind of trick? And theoretically, you can call any kind of function with any number of the arguments with this technique, but we will learn about that in week 5 challenges. But in this week 4 challenge set, we will focus on calling 1 or 2 or 3 functions as a chain. Oh no, we will just cover calling 2 functions in the chain. Yeah. And then 3 and more will be the week 5 thing. Yeah. Any questions about this approach? So if you got confused, get back to this slide and then play it again and again, or play the video, yeah, then you will get the idea about like how you can set the arguments for that. And then in the environmental variable, there will be always shell variable that stores /bin/sh. So you can always find the bin/sh string in the program's address space. So what's the matter for you is get the system address, get the bin/sh address, put that accordingly. So the assignments are, so DEP1, you need to run some function in the program. So this is the easiest one. You don't need to play with this kind of trick. You just need to call one function in the program, similar to the get shell. And then it requires a little bit of trick because some function does not do anything meaningful for you, but you can still run bin/sh. So think harder for that. And then for DEP2, there's no sum function. You need to run system in the library. So please go back to the slide, play it again and again, understand that, and attack DEP2. And DEP3, I intentionally removed all dynamic library to make the challenge harder. It's not that hard. So in the program, it has some functions that you can utilize. So the hint is some function opens a file, and then that file must be a flag. So you need to call some function first to open the flag file. And then, so read function requires the file descriptor for choosing the file, but in almost all of the systems, the de facto standard is file descriptor 0 is for standard input. File descriptor 1 is for standard out. File descriptor 2 is standard error. So the reason why I explain this is that the first file you will open will always have file descriptor number 3. So with some function, you can open the flag file. You don't have to worry about the file descriptor for the flag file because that will be always 3. Yeah. So what you need to do is read from the file descriptor tree, that's the flag file, and then read that into some of the stack address that we don't use for the size for longer than the flag. Then it will read to the memory, and then if you call printf with that address, then it will print the flag for you. So the DEP3, it's not about the executing the shell. You need to call multiple functions to open the flag, read the flag, and print the flag out. Yeah. So it will never give you the shell. Actually, you can get a shell with a little bit more techniques. Yeah. Then I believe the challenge will be 5 times difficult. Yeah. But you can read the flag with these tricks. And then there are some slides for that. So one of the hints is that the sum function opens a.txt. So it opens a.txt, but now we know how to play with the file name. So you can have a symlink to flag to a.txt. Then some function will open the flag. So the exploit sketch is something like this. So we will call 3 functions. With some function, we will open the flag.txt, a flag as a symlink, and then there will be a file descriptor tree, and then we will call read 3 some stack address and the length. Then it will read the flag, and then later we will call printf the address, same address. Then we can print the flag. So you might, when you're tackling this challenge, you might feel that with this kind of the buffer overflow, you are actually writing a program. You can call any kind of function. So it's not C language, return address language. Yeah, you're actually writing the program for that. Then that technique is so-called return-oriented programming, and that is the topic for week 5. Yeah, but in week 4 challenges, we are preparing for that. So if you fill the buffer like this, so this is the return address. So it will first call some function, and then if some function returns, it will return to the read. The read first argument is 3. Second argument is address. Third argument is the size. So we call read with these 3 arguments, and then it will return to printf. And then the first argument for the printf is luckily the same as the address. Then it will print the flag for you. So set the stack like this, then you can win. Any questions about the data execution prevention challenges? So basically, you need to call existing functions. And to do that, you need to set the arguments. So week 4 has 2 phases. So I set the due date as longer than the other weeks. So the due date is the February 22nd. Yeah, you will have plenty of time. Yeah. So in the first phase, today, I release these 7 challenges in VM CTF1 server. So DEP 123 and the stack cookie 1, 2, 3, 4. And then like it's quite different things. So like I cannot tell which one is difficult. So just try it in any way. But in the numbering order, the difficulty goes up. Yeah, that's the thing. And then that's the first page. And then on Wednesday, I will release 6 more ASRL challenges. I will cover that in the next lecture. But our VM CTF1 server, I intentionally disable all the randomization. So for week 4 first phase, we will use VM CTF1 server. But after that, for the second phase and week 5, 6, 7, we will not use VM CTF1 server because that would be too easy. Yeah. So we will move to the VM CTF2 and VM CTF3 server to tackle with the randomized challenges. Yeah. So for that, we will use a different server. So challenges available for now. So if you want to tackle that without taking my lecture, yeah, great. Yeah. Then to do that, you need to connect to the VM CTF3 server using the same credential. I copied all the public key to the same the server, same public key to the server. So just change VM CTF1 to 3, then you can get onto the server. And then right now you have like an anonymous like the what is that mask screen when you log into the VM CTF1, and then in VM CTF2 and 3 there will be different image. So you will immediately notice like, oh, this is a different server. Yeah. Any questions? Oh, today is a good day. No questions. Yeah. So then please work on the challenges, or you can leave if you want so, or like play with the challenges. And then like I will update our challenge scoring server later today. So like you will have like the challenges on the scoring board in before 2 p.m. Yeah, I'll do that. Sorry about my procrastination. Yeah. So, but you can still get the flag and then store that.